Namaskar, a very pleasant evening and a warm welcome to the distinguished guests, principal, faculty, delegates, and my dear friends. On behalf of St.Ann's College for Women, I, Dr. Santoshi Mishra, a proud member of the department and Dean Student Affairs for the undergraduate program, take this privilege in welcoming you all to the national level lecture series, Igniting Young Minds Towards Mathematical Research. Mother Teresa rightly said, prayer is not asking. Prayer is putting oneself in the hands of God at His disposition and listening to His voice in the depth of our hearts. Let us begin this wonderful evening by invoking the blessings of Lord Almighty. May I invite Mrs. Saujanya, Assistant Professor, Department of Mathematics and St. Anne's College for Women, to lead us into prayer.
Thank you, ma'am. The Bible reading for today is taken from Isaiah chapter 55, verses 10 to 12. My word is like the snow and the rain that comes from the sky to water the earth. They make the crops grow and provide seed for planting and food to eat. So also be the word that I speak. It will not fail to do what I plan for it. It will do everything I send it to do. You will leave Babylon with joy. You will lead out of the city in peace. The mountains and hills will burst into singing, and the trees will shout for joy. This is the word of the Lord. Thanks be to God.
Thank you. Mathematics is the language of the universe. It expresses itself everywhere, in almost every facet of life, in nature all around us, in the technologies surrounding mankind. If there is any subject that can be used to understand the complexity and intricacy of nature, it is mathematics, which has branched into various fields of sciences and in itself is a world of perfectness and infinitude. Mathematics is used throughout the world as an essential tool in many fields, including natural science, engineering, medicine, and in data science. Research in mathematics is the process of trying to find answers to interesting math questions. These questions might have applications to daily life, or they may be studied solely due to their intrinsic interest. Math research is usually very challenging, but it is immensely rewarding, intellectually satisfying, and intensely beautiful. Well, in our exciting journey towards understanding, exploring, and rationalizing the significance of mathematical research in igniting young minds, undergraduate students, and the process of visualizing, navigating, and evaluating its importance by our eminent speakers from reputed IIT institutions, let us proceed towards virtual lighting of the lamp. Light is the universal and fundamental symbol of spirituality and divinity. It is an illuminating source of goodness, purity, and is the dispeller of the darkness. Light reflects auspiciousness, prosperity, and a metaphor for the transformation involved in the quest for enlightenment. Do join us in the virtual lighting of the lamp.
Shubham kurutvam kalyanam arogyam dhanasampada.
Thank you, dignitaries, for joining us at the virtual lighting of the lamp. Mathematics research provides students with an understanding of what it means to do mathematics and of mathematics as a living, growing field. Students develop their own mathematical aesthetic and they practice making choices about which aspects of a problem to investigate. They develop both confidence as mathematics thinkers and enthusiasm towards the subject. The creativity, problem solving, and accomplishments that are part of research help to answer students' questions about the value of studying mathematics. Well, to dwell and have a deep insight about mathematical research and applications, we have amidst us the eminent speakers from Indian Institute of Technology, India. We have the pleasure of welcoming Dr. A. Sairam Kalaraj, Assistant Professor, IIT Ropar, Dr. Subhash Martha, Associate Dean Student Affairs, IIT Ropar, Dr. Satyaprakash Singh, Assistant Professor, IIT Kanpur, Dr. Tapas Chatterjee, Associate Professor, IIT Ropar, Dr. Jitendra Kumar, Professor, Head Department of Mathematics, IIT Ropar, Dr. Vikas Vikram Singh, Assistant Professor, IIT Delhi, Dr. Dutika Watts, Assistant Professor, IIT Kanpur. We welcome the dignitaries to St. Anne's College for Women on this virtual platform through virtual floral greetings. Kindly accept our greetings, dignitaries. Dr. Sister P. Amar.
Shubham
Dr. Sister P. Amrita is a PhD in mathematics from Osmania University, a proud alumnus of our college and recipient of numerous prestigious awards. To name a few, Global Peace Award, Mahatma Gandhi Peace and Harmony Award, Global Education Leadership Award, and Honorary Degree of Doctorate by the University of South America, and Devang Mehta Award. Sister has tremendous contribution towards research in the field of mathematics. I take this opportunity to invite our mentor, philosopher, and inspiration to St.Ann's family, our beloved principal, for the welcome address. Welcome, sister.
Thank you, Santoshi. A very good evening to all enthusiastic participants of this national lecture series on igniting young minds towards mathematical research. What an opportunity for students to get exposure to such distinguished faculty. It gives me immense pleasure to welcome learned academia. What a respiratory of intellectual health Department of Mathematics is creating. St.Ann provides an environment conducive to active learning and personal growth with the excellent human and material resources, progressively value addition through research, industry, and social interface ensures that our students get the best campus experience. We strive hard to impart academic training which could foster sound character building, develop critical thinking skills, instill in students a lifelong sense of participation and involvement in development of society and nation building. Undergraduate mathematics research is an excellent way to connect with experts, to take on projects, to be hands-on with emerging possibilities and challenges, catering to novel ideas in this field of mathematics. We have a rich tradition of organizing academic events by inviting expert resource persons, and this week has become one such special week by the gracious presence of eminent IIT professors from across the nation. The lecture series would help students develop the necessary proficiency skills and knowledge towards application-oriented research in varied disciplines of mathematics, which could create the required enthusiasm and zeal to pursue their career in mathematics, broadening their intellectual wisdom. I once again welcome all the speakers and congratulate the Department of Mathematics for this innovative initiative. Let's get started. Welcome and best wishes. God bless you all. Have a nice week with a series of lectures from IIT professors. Thank you.
Thank you, sister, for your kind and motivating words. Dr. Smita Asthana, IQAC Coordinator, Dean Academics, Accreditation Ambassador, is a passionate teacher, role model, and inspiration for many youngsters, definition for success, and epitome of perfectionism, and a strong pillar of St.Ann's, leading the institution with 3 cycles of NAC magnificent grading over the years, has more than 35 years of teaching experience. Ma'am has been the recipient of various prestigious awards. Her tremendous contribution towards the field of education and research in organizing conferences at national, international level, undertaking research projects, publishing books, research articles, etc. is ceaseless. May I have the privilege of inviting Dr. Smita Asthana, Dean Academics, to address the participants. Over to you, ma'am.
Thank you so much, Dr. Santoshi. It has been an absolutely exciting to hear so much about maths. I'll confess that I have a great love for subject of maths, though not good at it, but definitely appreciate all those wonderful people who have gained mastery in this. So what an opportunity for students to interact with such a learned professor, masters in numbers, magic in their hands and in their minds. I wholeheartedly welcome all the distinguished resource persons to St. Anne's. St. Anne's has been working for almost 40 years, and various areas are covered in our day-to-day life to give different kind of experiences to students, different exposure to students sitting on both sides of the camera. And as everything has some takeaway, I think one of the major takeaways of pandemic had been on these virtual platforms. Otherwise, where we would imagine that we will be able to face talk, learn, interact with such people. So that is one of the biggest learning that we have. As St. Anne's took full advantage of the situation and have created an environment where everybody is most welcome. Graded as an A+ grade by NAC, as College with Potential of Excellence by UGC. It's a mentored institution by, again, UGC under Paramarsh scheme. All our doors are open to everybody. It's an open learning door. It's an open door policy. So I congratulate once again all the participants to getting this opportunity to listen to such wonderful resource person. Congratulations to participants. Congratulations to organizers. And I'm fortunate to be part of it. All, thank you.
Thank you, ma'am, for your encouraging words. Dr. Nirmala Xavier, PG Dean, Head Department of Mathematics, St. Anne's College for Women, is having over 33 years of teaching experience, both at undergraduate and postgraduate level. Ma'am has been the source of motivation to young minds in excelling in the field of mathematics and pursuing higher education since decades. The mastermind behind starting MSc Mathematics at St. Anne's College for Women and Math Minds Coaching Center for various competitive examinations, which stand as a bundle of learning resource to math students, career-oriented courses, interdisciplinary courses in mathematics for students from other streams, instrumental in clearing several competitive exams. A math wizard, her passion towards subject is seen with diverse research articles published in high-end journals, both at national and international level, with her disciplined, dedicated, and unwavering professionalism. Ma'am has been instrumental in organizing various workshops, conferences, guest lectures, seminars, symposiums at national, international level. Ma'am has been resource person at several prestigious institutions, one among them being Wipro Consultancy in collaboration with BITS Pilani for software professionals. Ma'am has been the recipient of prestigious Telangana State Best Teacher Award on September 5th, 2021 for her tremendous contribution towards the field of mathematics. Ma'am has served as convener for important committees at St. Anne's College, being influential to the young staff. May I have the privilege of inviting Dr. Nirmala Xavier to give us the preamble of the national event. Over to you, ma'am.
Thank you, Santoshi. A warm evening to one and all. It gives me immense pleasure to welcome you all for the national level lecture series, Igniting Young Minds Towards Mathematical Research by eminent IIT professors from across nation. Department of Mathematics launched its journey after 2 years inception of the college in 1985 with MPC course comprising of 40 students and marched ahead with sincere and dedicated efforts of the teachers. With a sizable number opting for post-graduation in mathematics, department introduced MSc Mathematics in the academic year 2005-06. Demand in data science added a new feather in the cap, mathematics, statistics, and data science combination in the year 2020. Currently, department is proud to have 5 combinations, MPCS, MECS, MSCS, MPC, MSDS, with 600 students pursuing mathematics. With the motto of integrating my infinite limits, Department aims at a larger move towards generality and unification in mathematics to develop theoretical knowledge and computational experience for the benefit of student fraternity. Research in mathematics helps students to develop higher order thinking skills and problem-solving techniques in enhancing their perception towards an overall development and growth. With this objective, department has taken the initiative towards conducting national level series, inviting eminent IIT professors as resource persons in sharing their knowledge and expertise with our undergraduate students, enabling them to develop creativity, confidence, and necessary wisdom to pursue their research career in the field of mathematics. I wish students all the very best and expect them to avail this platform for a productive approach to gain constructive research knowledge. Thank you all.
Thank you, ma'am, for that comprehensive report. As we come to an end of the inaugural session, on behalf of the Department of Mathematics, St.Ann's College for Women, I take this privilege in proposing vote of thanks. I would like to thank Sister Principal, Dr. Sister P. Amrita, and Management St.Ann's for providing us an opportunity to organize the national level lecture series in reaching out to students beyond academics and broadening their perspective towards research in mathematics. I thank Dr. Smita Asthana, Dean Academics, IQAC Coordinator, St.Ann's College for Women, in rendering the necessary strength and support. My heartfelt gratitude to our eminent professors, Dr. A. Sairam Kalaraj, Dr. Subhash Martha, Dr. Satya Prakash Singh, Dr. Tapas Chatterjee, Dr. Jitendra Kumar, Dr. Vikas Vikram Singh, Dr. Jyotika Vats, in being generous to accept our invitation and be a part of the national level lecture series, Igniting Young Minds Towards Mathematical Research. Thank you, dignitaries. My sincere thanks to Dr. Nirmala Xavier, Head Department of Mathematics, St.Ann's College for Women, in being influential and the driving force to organize the national event for the benefit of student fraternity. I thank Dr. Sabha, Mrs. Japmala Rani, Mrs. Balasaujanya, Mrs. Navya, and Ms. Sana, my team members, in taking up the initiative of meticulous planning and carrying out the process of work diligently and effortlessly. Thank you, dear friends. My sincere thanks to our technical director, Mrs. Aparna, for her consistent support rendered. Last but not the least, Lord Almighty, for always standing by us. May I request the dignitaries and participants to please switch on their videos for a quick photograph. Navya, please take pictures. Thank you. We will now be proceeding towards the session by Dr. A. Sairam Kalaraj, Assistant Professor, IIT Ropar, on applications of linear algebra in real-world problems. May I invite Dr. Sabha to take over the session, ma'am?
Yeah. Thank you, Santoshi. Moving towards the first lecture, linear algebra and its applications. Linear algebra is the subfield of mathematics concerned with vectors, matrices, and linear transforms. It is a key foundation to the field of data science, machine learning. The ingrained use of linear algebra, notations, and methods in the subfield, such as deep learning, natural language, processing, and recommender systems, is very much recognized. To enlighten us more on the topic, linear algebra and its applications in the real-world problems, we have in our midst an eloquent speaker, Dr. A. Sairam Kalaraj, Assistant Professor, IIT Ropar, Punjab. Charismatic speakers are knowledgeable about their subject. They relate their topic to the broader scheme of things. They are expansive, inspiring, and uplifting. We are honored to have one such charismatic speaker amongst us, Dr. Sairam Kalaraj. Sir received his doctorate degree in mathematics from the Indian Institute of Technology, Madras. His field of specialization was complex analysis and function spaces. Sir's areas of interest are harmonic mappings in the plane, linear and affine invariant families of sense-preserving harmonic functions, Hardy spaces on the unit ball in C. Dr. A. Sairam Kaliraj has a sum total of 16 years of experience in teaching and research in the Department of Mathematics, Indian Institute of Technology, Ropar, Punjab, NBHM Postdoctoral Fellowship in ISI Chennai Center, Visiting Scientist in Indian Statistical Institute, Chennai, CSIR Junior Research Fellow in Department of Mathematics, IIT Madras. Dr. Sairam Kaliraj is recipient of many scholarships and awards, to name a few. Awarded postdoctoral research associate position for a period of 1 year at Texas Tech University, Lubbock, USA. NBHM postdoctoral fellowship, ISI. Visiting scientist position at ISI Chennai Center. NBHM research fellowship and CSIR junior research fellowship. Gold medal for securing first place in MSc Mathematics. Sir has 13 research publications in national and international journals to his credit. Looking forward for his talk, I invite Sir to take over. Sir.
Sir, we have made you the co-host. You should be able to unmute and share, sir. Just please try once.
Yes, yeah, okay, yeah, just, yeah, now it is unmuted. I think it is audible.
Yes, yes, sir. You are audible, sir.
Okay, yeah, fine. Maybe I will try to share my screen.
Yes, sir.
Navya, can you please stop sharing, Navya?
Yeah, so are you able to see the Mathematica page?
Yes, sir.
Yes, sir.
Okay, fine, thank you. Yeah, first of all, I thank the organizers for arranging this wonderful program, and I thank Professor Nirmala Xavier ma'am for inviting me to give a talk in this program. And apart from that, I thank and congratulate the whole organizing committee who has taken a lot of effort to arrange this event. So with this, I will move on to the topic. So the problem I am going to discuss today is related to some real world problem which highly rely on linear algebra. So basically we have we started studying linear algebra from the high school level onwards, starting from the basic matrix operation, how to add and multiply matrix and so on. So the basic motivation given for studying linear algebra is by considering system of equations. So we usually consider a system of equations in some 2 or 3 variable, and then we will try to solve the system of equations. So this is how the linear algebra or the matrix theory has been introduced to us in the school level. Even after coming to college also, we usually get accustomed to that kind of motivation and introduction, and then we will move on to study the properties of vector spaces and so on. So this is how people usually studied linear algebra. So in this talk, I am going to give a different perspective of this matrix analysis or linear algebra. So here I am going to discuss about image processing. So we have like taken or seen several photographs, videos, and so on. And nowadays, due to the innovation coming in the digital devices. Everyone is having a mobile phone with a camera which is already present in that phone. So we used to take a lot of photos and we enjoy such things. But have you ever thought how these things are working, like how these images are stored or how these images are processed? Like if you want to do some modification in the image, how the software is doing all these changes. So if you ask these kind of questions, the answer will come. All these things happens with the help of linear algebra only. So with this brief introduction, I will move on to the main topic. So we usually consider a general m by n matrix with some real or complex valued entries. So here I am going to consider a matrix. Okay, so the first thing I have given here, I will try to explain each and everything with the help of Mathematica so that it will be easy for understanding. So basically, if you look at this quantity which is available inside, this is the coding to write the matrix 0, 1, 0, 1, 0, 1 and 0, 1, 0. So after this, I won't read all the matrices, just for understanding purpose I have read. So if you consider this matrix, this is the first row of the matrix. And this 101 is the second row of the matrix. 010 is the third row of the matrix. So if you try to use this command image and use this matrix, you can see this picture. So here you can see, like wherever 0 comes in the matrix, you can think of this as a 3 by 3 matrix. So wherever 0 comes, you can see at that place this dark black color dot or black color square. And wherever 1 comes, in that you will be seeing one white color square. So for understanding purpose in computer terminology, we used to say like one small piece of a picture as a pixel, or okay, we can consider that as a dot. So how these images are formed? So here I have given an example of a black and white picture. So in this picture, you will be using only two colors, black, the extreme black and the extreme white. So for black, we will be like, if you put 0, it represents the black dot. And if you put the number 1, it represents the white dot. So there is something else we can look at it, like this is the image of a black and white picture, but if you see, there are color pictures as well. So in order to understand color picture, I will introduce a similar notion of a matrix correspondence to the picture. So here I have given a different matrix. So you can think of like in the first matrix, I have given this matrix. So if you see this, actually this is representing a 3 by 3 matrix. So I have started with a flower bracket and ended this with a flower bracket. So if you see each of this thing, it represents a row. But in the second thing, if you see this 100, this itself represents a single color. Actually, if you want to study about color pictures, there is a very interesting phenomena happens in this computer science. Like every color can be generated with some kind of fundamental colors, which are red, blue, and green. So if you see a color picture, as we have done in the black and white picture, the 0 represents black and 1 represents white. In color picture, if you put one single dot, that dot can be of any color which is available. So any such color can be generated or obtained by combining these three color, red, blue, and green, in a particular ratio. So here all these colors, red, blue, and green, if you try to see, it will vary from 0 to 256. Actually, what I'm saying is in computer language. So if you put 0, it represents a very light version of that. Or, oh, sorry. Actually, if you put 0, you can understand that that color is not mixed while forming the color. Okay. Maybe I can explain this first one. First triplet is 1, 0, 0. So what this represents is, in a color picture, the first dot is formed by taking red color and no blue color and no green color and no blue color. Okay. So if you see the second one, 0, 1, 0, in this, it is the second dot because it is coming as the second element. So the first component represents red. So there is no red mixture in this dot. The second one represents green. The third one represents blue. So since the other two components are 0, it is appearing as pure green color. Okay. So actually, if you see any color, it will have various intensity. It can be very light, or it is not at all part of that dot. Okay. So the intensity will vary from 0 to 256. If you put 0 at a place, it will represent that particular color that is among this red, green and blue, corresponding to that, like first coordinate represents red, second represents green, third represents blue. If you put 0, we understand that that color is not part of that mixture. If it is 256, the highest intensity of the color is available in that mixture. So that's what we will be interpreting. So yeah, here is another example. So I have drawn 6 dots with various color combinations. So now let me take one picture, which is default picture available in the Mathematica site itself. So here is a picture of a woman. So if you see, this is a color picture. So let us try to see what is the dimension of this picture. So if I try to compute the dimension of this picture, actually this matrix, this picture is formed by a huge matrix of dimension 150 cross 116. That means this contains 150 rows and 160 columns. And if you try to see how many elements are there, actually 17,400 triplets are there. That means 17,400 triplets. Each triplet will represent a single dot. So 17,400 dots forms this single picture. So maybe for understanding purpose, if I try to put all the data, it will be like very huge. So I will try to take first 5 rows and first 5 columns of this picture. Okay. So here I have given the matrix form of the first 5 rows and first 5 columns. Okay. So here, if you see the first dot, so actually you can see it is 240, 162 and 98. So that means the intensity of the red color is 240, intensity of the green color is 162, and the intensity of this blue color is 98. Okay, this different intensity of various colors will give you or give rise to different colors. So this is how this image has been formed. Okay, now, yeah. So it can be written in various different formats. Now I want to take some color separation. That means if I use this color separate, actually what it do is it will take the first component separately, second, like in each vector, it will take the first component, that is 240, 246, 236. So it will take all the red component and form a matrix. Okay. So if I consider the image corresponding to that, I am getting this picture, the first picture. So a person can ask the question, we have considered only red component, but why this picture is not coming in red color? Actually, once you separate and simply put a single component, like if you put it as a m by n matrix where each coordinate is a single real number, then it will consider that as a grayscale image only. So due to that reason, even though we have separated the red component, when it try to interpret, or when the system tries to draw the picture, it will have real number at each point. So if it is completely zero, it will take it as black. If it is 256, it will take it as white. And in between numbers, it will try to vary the intensity of the white and black. So the second thing corresponding to the green color, and the final thing corresponds to the blue color. So it has been separated. So if I want to work on with color images, I have to do some complicated computation in which I have to manipulate all the three different coordinates in this each element. But for a basic lecture, and to make the lecture more understandable to every audience, I would like to take a single component, that is a grayscale component, and I want to proceed further. Okay. So now I have taken some matrix corresponding to one coordinate. So I have named that matrix as A, and image corresponding to A is given like this. So this is the image which is corresponding to A. Now, so I am going to give several nice operations which I can perform on this matrix. So I am using this command, take this A 30, 90, 30, 120. So what this command will do is, it will take the rows from 30 to 90. So it takes the rows from 30 to 90 and columns from 30 to 120 from this image. So let us see what it gives. So if you try to see, the full image has a bigger image. Like if you see the full image, the hat is coming up to here, and left hand side and right hand side we have so many other things which are visible. But if I try to cut down the matrix within these rows and columns, I am trying to get a particular piece of that picture. So you might have used several softwares, either in your laptop or computer or in your mobile phone, to edit pictures. So actually, how all these photo edition has been done, actually there is a software which is running in the background, which was coded using some programming languages, but the computation what they do when we perform certain action, that has been done with the help of this linear algebra only. So whenever you, like if you take a paint or some software, and if you try to crop a image, when you put your cursor at some point and try to drag it where you put your cursor first, that will be taken as the starting row and column element. Okay, so for example, here I have used 3090 and 30/120. So the element corresponding to 30, that is my starting point, and the ending point is corresponding to the 90, 120 element. Okay, so whenever you put your mouse or any like pointer on that photo and you press click, it will note down the row and column number corresponding to that point, and this is how the cropping is done. And similarly, if you try to ask the question, okay, I have the matrix A, so what will be transpose of A? Okay, so if you try to see that kind of thing, you will be able to see it will be some kind of rotation. Okay, maybe I can try to do that. Okay, so this is the command. If I put transpose, it will take transpose of the matrix. Okay. So now you can see what happened to this picture. So if you try to enlarge the picture, you will be able to see certain things. So actually in transpose, these rows and columns will be interchanged. So how it has become. So actually if you try to interpret, you will be able to see that there is some rotation happening. So actually it has rotated by 180 degree, I think. Yeah. Okay. Actually it has rotated by like it has rotated and the reflection of that rotation has been taken. So this is how the transpose operation helps to change the orientation and it reflects the picture. So basically, if you try to do this kind of operation, when you try to rotate it by certain degree, there are some other complicated matrices will be involved in that. So it will try to move the points to a different position. Yeah. So next, I want to consider a special kind of decomposition in matrix theory, which is called as singular value decomposition. So if you have not studied a singular value decomposition, you don't need to worry. Just you can simply follow with a simple assumption. So if you are given with a matrix which is a square matrix, if you are given with n by n square matrix, you know how to do this diagonalization. That means all the matrices are not necessarily diagonalizable. There are some matrices which can be written as a product of three matrices, where the matrix which comes in the middle will be a diagonal matrix and you will have the other matrix. So if you have a matrix A, it can be written as P, B, P inverse, where B is the diagonal matrix and P will be a invertible matrix. So you know how to do the diagonalization, provided if the matrix is diagonalizable. But if you try to see that, we can speak about this diagonalization only for a small class of uh, matrices only, which are diagonalizable. Otherwise, we cannot write that matrix in that form. But there is a generalization available, which is called as Jordan decomposition, which is the generalization of diagonalization for all n by n matrices. So I am not going to that also. So there is a similar kind of idea or decomposition, which is popularly known as singular value decomposition, which can be done for any m by n matrix. That is, you take any rectangular matrix, then that rectangular matrix can be written as a product of three matrices. So maybe I will try to give some basic introduction about that singular value decomposition, so you will get a feel how to do it. Okay, so here I have given an example for singular value decomposition. So here I have given a matrix which is having 2 rows and 3 columns. So basically for this matrix, we cannot try to find eigenvalue, eigenvector. We cannot do that because this is a rectangular matrix. But whatever rectangular matrix we are given with, you can try to do this AA transpose. Either you can do AA transpose or A transpose A. Both are going to be meaningful. So if A is m by n matrix, then if you look at A transpose A, this is n by m, multiplied with m by n. So your final product will be equal to a matrix which is of dimension n by n. So similarly, if you consider this matrix A transpose, this will be a m by m matrix. So irrespective of the size of the matrix A, if you calculate A transpose or A transpose A, both are going to be a square matrix. So for this square matrix A transpose A and A transpose, we can find what are all the eigenvalues and eigenvectors. So that's what we are doing here. For A transpose, I am calculating the eigenvalues. Then I am taking square root of that eigenvalue. So since this A transpose, if you look at this A transpose, it is possible to prove that whatever may be your matrix A, this A transpose, all the eigenvalues of this A transpose must be non-negative. That means the eigenvalues must be greater than or equal to 0. This is a property. So therefore, I can take the positive square root, which is meaningful. So all these positive or non-negative square root, if I take, it will come as a real number. So the next step is I have to find the eigenvectors corresponding to these matrices. So here I have computed for A transpose. Similarly, for A transpose A, we can find the eigenvalues. So if you try to see if m and n are not equal, obviously one of these A transpose A or A transpose, one will be having the smaller dimension. Okay, because one is of dimension m by m, the other is of n by n. So due to that reason, for one matrix, you will be getting two eigenvalues, and for the other matrix, you may get more eigenvalues, but there is a nice relation between these eigenvalues. So actually, if you see the non-zero eigenvalues, so the non-zero eigenvalues for both A transpose and A transpose A, both are going to be same. So that is a nice property of these matrices. So it is not only happening for this matrix, for any matrix A, if you calculate the eigenvalues for A transpose A and A transpose, you will be able to see their non-zero eigenvalues are going to be same. Okay. Then the remaining eigenvalues for the bigger matrix will be only 0. Okay. Now what we can do is we can try to calculate the eigenvectors corresponding to this, and then we can proceed. Actually, if you look at this thing, I want to emphasize one more thing. So people may ask, so we started with some matrix and we are proceeding in this way, whether these matrices A transpose A are diagonalizable. The answer is yes, because this is a symmetric matrix. So therefore it must be diagonalizable. So due to that reason, I can proceed further and I will be able to do the diagonalization process. So here I am trying to find the eigenvectors corresponding to this. So I will skip those things. So it is possible to find eigenvectors which are orthogonal to each other. That means if you take the inner product or dot product of these two different eigenvectors, then the dot product would be equal to 0. So that is also one of the nice property of this. So I will be able to do that. So finally, I can do this kind of computation. I will be able to come up with this diagonalization, or I can find all these eigenvectors corresponding to this A transpose A and A transpose A and A transpose. And finally, so the thing is, I start with, it is possible to write A as like it is. I am assuming that it can be written as U sigma P transpose. So if I I will skip some of the things because then it will become very Like if I include everything, I may not be able to give all the important information about the application part. So I will proceed very casually, assuming certain things. So this is what I am doing, this transpose, and then multiplying with U sigma V transpose. So if I do this, this is nothing but V sigma transpose U transpose U sigma this V transpose. So finally what will happen, this is the property of this matrix U. This U transpose U will become I, and then finally what we will be able to get is this V, this sigma transpose into sigma. So if you try to see, this is a diagonal matrix, this sigma is a diagonal matrix. So when you multiply, you will be able to get this square, this whatever eigenvalue we got, we will be having here, this 25 and 9. So this is the relation we are getting. Like if you try to get A transpose A, then what we are getting is it will come in this manner. So due to this reason, we are trying to calculate, like I am going in the other way. Actually, I am not proving that any matrix A can be written in this form. So I am just assuming, and for making people get some feeling about how we are doing the computation, I am going in the other way. So finally, after computing these eigenvalues and eigenvectors, and by using this relation, I will be able to find the matrix V. So then what I can do is, so this is how I got the eigenvectors corresponding to that A transpose A, I think. Yeah, A transpose A, and I found the orthogonal vectors and I formed this matrix. So I need to calculate U also. So I can use a similar approach, A transpose, and I can do a similar computation and get U as well. But there is one more approach which is available if you try to study the property of this singular value decomposition. We will be able to see that if you write this capital U as U1, U2, like each element Ui is a column vector. Okay, so if you write in this way, you will be able to see that this Ui has this property. Here this sigma is the singular value, which is square root of the eigenvalue of A transpose A. So if you multiply this singular value with Ui, it must be equal to this A, the matrix A multiplied with the vector Vi. So this is a nice property, like this can be used to calculate Ui without doing much computation. Like we don't need to calculate the eigenvalue, eigenvector for A transpose. Using this simple phenomena, you can get what is U. So this is the working method for calculating the singular value decomposition corresponding to a given M by N matrix. So whatever may be the order of the matrix M and N, you can use the same procedure, like finding A transpose A transpose, and you can calculate the eigenvalue, eigenvector, and finally you can come up with this kind of representation. The beauty of this singular value decomposition is this singular value decomposition can be done for any M by N matrix. So that is the beauty. Any M by N matrix can be written in this form. So with this, I will go back to my picture. So maybe I can try to say some more interesting thing about this. So actually, if you try to see if your picture is very much bigger, correspondingly you will get a bigger this diagonal matrix. Okay, so if you try to see, there is a way to write these diagonal entries. So whenever you try to calculate this diagonalization or diagonal representation of a matrix. Like if a matrix is diagonalizable, we simply calculate eigenvalue, eigenvector, and we will try to put in some random order. So here I want to emphasize one more thing. So whenever we do singular value decomposition, we usually try to arrange these singular values. Singular values are nothing but the square root of the eigenvalues of A transpose or A transpose A. So we will always try to write the singular values in the descending order. That means the highest singular value, the largest singular value will be written in the cell one by one. In the matrix one by one it will be written. Then you will be having the next largest singular value. So we will always try to write in this descending order. Then accordingly we will be computing the matrix V and so on. So there is a very important consequence of this thing. So that I will try to explain with the help of this picture. So the thing is, if you try to see this largest singular values, this will capture most important information of the picture. Okay, so that means, so if you try to see each picture of different person, their face will be looking in a different way. Like my picture will be different from picture of another person, the face. Okay, so what is the important changes which will distinguish the picture of my face with the picture of other person face? That will be captured by these largest singular values. So basically we will be able to write this in a different way as well. Maybe I will try to give. So here is a handwritten notes I have prepared. So actually if you try to see this can be written in this format. Okay. So maybe I can go back and write in that way. I can write this as summation I equal to 1 j equal to 1 to n sigma j uj vj transpose. Okay, here this u1 u2 are the, like I can write the u matrix u in this format where u is the first column, u2 is the second column, uj is the jth column. Similarly, if I see v transpose, I can write in a similar way. So this will correspond to the particular row. Okay, so the same matrix A can be like after multiplication. This is the other way of writing the matrix after doing the multiplication. So if you try to see, if I write the singular value sigma 1, this is the largest of all the eigenvalues, then sigma 2, then sigma 3 and so on. Okay, so if I try to arrange in this way, what will happen is the most important feature of that picture will be captured by the largest eigenvalue into this element. That means the most important information about this picture will be obtained by finding what is the product of u1 and v1 transpose and multiplying with sigma 1. So if you try to see, this itself will be a m by n matrix, because u is a column and vi transpose, that will be a row. So if I try to multiply this, I will be able to get a m by n matrix. and this itself will give the most important information of that picture. Okay, so if I try to explain this in a proper way, then at the end I can say several analogous applications which are very much popular in artificial intelligence, machine learning, and so on. So actually this singular value decomposition has several applications. So what is the advantage of this? So my original matrix A can be written as this summation of this varying from j equal to 1 to n. But if I take only finite summation up to k, where k is strictly less than n, that is not exactly equal to a, but what it will represent. Okay, so my a is equal to this. So I define a new matrix AK. Okay, so this is equal to j equal to 1 to n sigma j uj vj transpose. Okay, so if I see this AK is not exactly equal to A, because I have taken this K to be strictly less than N. So in this case, AK is a different matrix. So let us try to see what it represents. So we will try to see this with the help of this picture. So here I have already mentioned this picture has dimension 106, 100. I think I have done it in the beginning, 150 cross 116. So what I am doing is I have done the singular value decomposition of this picture. That means I have taken this grayscale image. For that grayscale image, I have done the singular value decomposition. So when you do the singular value decomposition, the Mathematica will itself will do in the same way as we mentioned. That means if you try to see how it arranges the diagonal elements, that singular values in the diagonal, it will write only in the decreasing order. Because of the application, the mathematician has made the importance of these singular values. So due to that application, this Mathematica as well as MATLAB and so many other softwares available in the market, they also used to write the singular values in the descending order. Now what I have done is I have taken the first 50 singular values. Okay, so with the first 50 singular values, maybe if you look at this one, this representation will be very much easy to you. Okay, so actually I may have so many singular values. What I am doing is I am finding a new matrix A50, which is done by taking first 50 non-zero or first 50 largest singular values. Okay, sorry. Sigma j uj vj transpose. So this representation is easy to say what is AK. Okay, so I found the singular value decomposition corresponding to the original picture. That original matrix representation for the original picture I considered as A. Then I have computed A50. So this notation will be very much easy for the computational purpose. Okay. So if I try to see A50, let us try to see how the image will look like. So now I have given this. If you try to take K, that means essentially in the center, that matrix which has diagonal elements non-zero, like similar to this example. Okay, here this is the matrix sigma, which has which is similar to the diagonal matrix in the diagonalization process. So here I will take first 50 non-zero elements. Okay, so if I try to do that, there will be several zero elements. So therefore, essentially, what I will be having is, I will be having only 15,800 numbers if I take k equal to 50. So let us try to see, if you consider the original matrix according to its size, if you want to send all the data, all the dots, colors corresponding to the dots, we have to send 17,400 data points or numbers. But if I use this A50, just I have to send only 15,800 numbers. By calculating this itself, I will be able to find what is A50. Let us try to see what is A50. Okay. So here I have the picture. So if you try to see, you cannot see any big difference between the original image and this image. Okay. So now you can understand what I mentioned by this AK. So even we started with A and then we tried to do this AK, J equal to 1 to K. Even though we did some truncation, if you try to see the picture, it resembles the original picture. Okay, so what is happening here? So let us try to calculate A40. A40 means we will take only first 40 largest eigen, these singular values, and then we will try to consider the matrix which obtained with the help of that first 40 elements. So if you try to see that image, you can see some little blurring. Like if you try to see A50 and A40, in A40 you can see some simple blurring. Okay, but what is the number of elements? If you send A50, you are essentially sending 15,800 numbers. But if you are sending A40, you are sending only 12,240 numbers. So you can see the difference, like original image has more than 17,000 numbers, which are very much crucial to make the picture. But with very less number of dots or information, we are able to get almost similar image, which has some small kind of blurring, but still with very less number of points, we are able to generate a similar picture. So here I have done A30, that means which has used first 30 largest singular values and the vectors uj and vj transpose corresponding to that first 30 singular values. So you cannot see very big difference between these things. Okay, but if you look at closely, you can see A30 will be having much more blurring. Maybe if you want to see much more blurring, you have to look at very few singular values and corresponding matrix. So I have taken A10. A10 means I have constructed the matrix corresponding to first 10 largest singular values. Here you can see a high amount of blurring, like compared to A30, A40, you cannot distinguish between the A50, A40, but if you try to see A10, you can see it has much more blurring effect. Okay, so the question is whether this happens only for this matrix, this picture, or it will happen for everything. So the beautiful thing is mathematician has proved that this is a result. So you can wonder how a mathematician can prove this picture will be similar to the picture generated by A. So that was the beauty of mathematics and linear algebra. So in order to do that, we need some more terminology. So you might have already studied what is meant by norm. So here I have given the pth norm corresponding to a matrix. So if A is a n by n matrix, we can define the pth norm of A in this manner. Supremum over x not equal to 0, norm of Ax with respect to P divided by norm of x with respect to P. So here I want to mention what is pth norm of x. So you might have already studied this if you have done some course on functional analysis. So if I have this vector x, which is equal to x1, x2, etc., xn, then this pth norm of x is nothing but summation I equal to 1 to n modulus of xi power p whole raised to the power 1 by p. Okay, if you look at this, it will look like the generalization of Euclidean norm. In Euclidean length, you will be taking modulus of xi square, then you will sum it up and take the square root. So instead of square root and second power, we will be taking the pth power, and after summing up, we will be taking the pth root. Okay, so this you can take for any vector. So the denominator is defined in this manner. So if you consider any vector x which is not equal to 0, then calculate what is Ax. Since it is a n by n matrix, if you multiply, again you will be getting a vector. Okay, so Ax is nothing but a vector. So for that also we can calculate what is the pth norm. Then we can compute this supremum, that is called as pth norm of A. So if you restrict yourself to vectors x such that norm of x is equal to 1, then it will get reduced to this form and all these things are equal. So since the time is very less, I will quickly go on to the other things. So this is the vector norm. So using this vector norm, we can define the matrix norm. That is what we have done in the previous step. Just in the right hand side, we used the norm corresponding to vector. Using that and taking supremum of this quantity, we have obtained or defined norm of a matrix. So if this norm satisfy the following inequality, that means for any matrix A and B in R power n cross n, that means if you take any two n by n matrix, if that satisfy this inequality, then we will call this as a matrix norm. So that means the question is whether all values of P, the above norm will become a matrix norm or not. Okay, so this is very important concept, this inequality, which is very much useful in several computation. So this is very much crucial. So for example, for certain values of P, we can have the formula to compute the norm. That means if your matrix is A, if you want to calculate the one norm, just you have to take maximum over all the columns. Okay, so you fix a column. For that column, you calculate this one summation over modulus of Aij. You do this for each column, column 1, column 2, and from that value you take what is the maximum. Just you have to calculate n summation. Among the n summation, which one is the highest one, that will be the norm of A if you take P equal to 1. Similarly, this sup norm and 2 norm are defined in this way. What I am interested in here is the 2 norm. Maybe I can use a different color. So if I try to see the 2 norm of A, this is coming out to be sigma 1, which is the largest singular value corresponding to the matrix A. Because if you try to see, it is the square root of this eigenvalue of A transpose A. Therefore, so we already studied what is this sigma 1. It comes as the largest singular value in the singular value decomposition. So the next comes is the very important theorem. So if you try to see Okay, I will directly move on to that theorem. So this is the very important theorem which will play the crucial role. So this theorem only guarantee that the matrix AK be obtained, that will be resembling, or that will be very much close to the original picture of A. So let us try to read the theorem and understand the thing. So A is any m by n matrix with real entries, and it has a singular value decomposition. So the singular value decomposition we will write in the same way. So that means A is equal to summation I equal to maybe 1 to n sigma I, or maybe I use the same notation, sigma j, this pj. Okay, here I used a different notation, qj transpose. So this is the original singular value decomposition. I have taken the truncation up to k and I have named that as ak. So what this theorem says is, if you try to see the difference of A and B, so where B is any m by n matrix, so A is m by n matrix, given a picture, you can convert that into a m by n matrix, okay, corresponding to the original picture. So what the question is, if you take any m by n matrix, it will also correspond to some picture. So whether two picture are having some relation or not, okay. So if this norm of these two picture are becoming very, very small, that means if you calculate the norm in this way, and if this norm is very small, or if it is very much closer to zero, then if you try to see the picture corresponding to this A and corresponding to that B, so if the norm of A minus B is very much closer to zero, if you try to see the picture, they are very much closer or similar. So what it essentially sees is, like if you have a element A in R power mn, maybe I can try to draw R2. So this is like not the correct way, but for understanding purpose. So you think of this A as a dot in the R power m cross n. So what this says is, if this is very much closer to zero, that means that matrix will be lying in the small neighborhood of A. Okay. So therefore, due to that reason, the picture coming is very much similar to the original matrix. So what this theorem says is, if you try to take the B which has rank k, so you know what is rank of a matrix. So the original matrix A has rank k. So if you try to, okay, the original matrix may have some rank. So if you try to take k which is less than rank of A, so if you consider all possible m by n matrices which are having rank k, then if you try to see minimum over this norm of A minus B, so that norm must be equal to the k plus 1th eigen, or not k plus 1th singular value in the singular value decomposition. Okay. So essentially it says that that is the best possible approximation of A. So this is like sigma k plus 1 is equal to minimum of this quantity. Actually, if you try to take minimum of this thing over all matrices B which are of rank k, the question is whether equality will be obtained for some matrix. That means, does there exist a matrix B for which the norm of A minus B is exactly equal to sigma k plus 1? So that is given in this next line. So when you take B is equal to AK, which we obtained in this manner, for this matrix, if you calculate this norm, this is equal to this one. So you can think of like this: A is a particular matrix. Okay. So what is the minimum distance, like if you try to see all the k rank matrices, it may lie like this. Like the original rank of A can be a bigger number, k plus 1 or k plus some L. So if you consider all the k ranked matrices, you will be seeing it will be lying like this. So what is the closest matrix which is of rank k, which is very much closer to A? Okay, so in other words, I can say what is the kth rank matrix which is best possible approximation of A. So this theorem says that the best possible kth rank matrix approximation of A is given by AK. In picture, we can say that the picture which has K if you consider AK to be the matrix obtained from the singular value decomposition of the original matrix, that is the best possible approximation, which has that many singular values of A, and it best to approximate the original picture. So yeah. So here I have given the proof, but there is only some 3 minutes left. So yeah, actually what we can do is this kind of things are very much useful in machine learning and other topics. I will quickly say something like there is like the important whatever data you collect, it can be represented in a matrix form. So as we have seen here, if you write the singular value decomposition, here we have seen the singular values and the corresponding pj qj transpose, which is corresponding to the highest singular values, that captures the important information of the matrix, the facial information of the matrix. So similarly, if you try to see any collection of data, if you try to write it in a matrix format, if you try to do the singular value decomposition, the first few highest or largest singular values and corresponding pj qj transpose will capture the important information available in the given data. So there is a study called principal component analysis, which will be a consequence of singular value decomposition, which will be helpful in extracting the important feature of a given data. Okay. Yeah, with this I will conclude my talk. Yeah, if you have any questions, you can ask.
Thank you, sir, for your informative and stimulating lecture. Floor is now open for question and answer session. If anyone wants to ask questions, you are most welcome.
Sir, I have a question.
Yes, ma'am.
Sir, the entire image processing, the back end of the entire image processing is run through matrices only?
Yes, ma'am. Yes, ma'am.
Like
so actually there are some, actually there are other,
Sir,
yes.
This example of, the image that you have shown, like, here we have seen, the image can be reversed and all, by using the matrices. But apart from that, can you just tell me, where and all it is applied? In the image processing?
Okay. No, actually, ma'am, in most of the things they use, like there are other tools also available to do certain operation. For example, this Fourier analysis techniques also usually used in the image processing. But mainly, if you consider any picture, like whatever picture you take in your photo, just you go to MATLAB or Mathematica, you like whatever I have shown here. Like maybe I will show you the code. So you store your picture in your computer, just you use this command import, like you give the location of the picture and try to take the picture. Okay. And otherwise, what you can do is you can place the picture in some folder and try to write matrix form of that image data. So if you try to do that, you will always get a matrix of this form.
Okay.
Okay. So all the images are stored in whatever application you use, it is stored in the matrix form only. And many of the operations are done with the help of this matrix analysis techniques. But of course, for example, if you try to, for example, in several movies, you might have seen something like there will be some criminal, some police will get the picture. They will try to match with the criminal data. Okay.
Yes.
So whether this picture matches with some other person's picture. So for to do that kind of study, they may use some other techniques as well. For example, there are some Fourier analysis techniques also available to do that job. But basically, if you have any picture, that is stored in the matrix form only. And most of the operation, for example, if you try to send a picture in WhatsApp, your picture may be of 5 MB, but when you send it to your friend, the other end person will not receive the original 5 MB, just to minimize the data, because crores of people will be using WhatsApp. If the data is very huge, then the cost of sending and the company which is having this WhatsApp, they have to run a huge kind of program, and it adds so much cost to them. So by default, WhatsApp and other things will use some kind of image compression, which is similar to what we have discussed now.
Thank you, sir. Thank you very much.
Yeah. Any more questions? Okay. On behalf of Department of Mathematics, I thank you, sir, for a power-packed session, enlightening us on applications of linear algebra. I'm pretty sure that your address has given our students a significant mathematical way of thinking. What you have explained is the singular value decomposition plays a vital role in the technology of image processing. Thank you once again, sir, for being with us today and addressing our students. Thank you, participants, for your unwavering attention. I request participants to fill the feedback form. The link is being displayed in the chat box. Thank you all. Let's meet tomorrow sharp at 4:30 p.m. for another learning session in applications of differential equations and numerical methods. Thank you all.
Yeah. Okay. Thank you.
Thank you, sir.
Yeah. Thank you
sir.
all. Yeah. Yeah.
Participants, please fill the feedback form. Link is being provided in the chat box.
Ma'am, link is provided in the chat box.
It's not opening for me, Navya, the link.
Not opening, ma'am.
No, that's what I was trying. I'll just try again.
Ma'am, once try again, ma'am.
Yes, I'm trying. Yeah, it's opening. It's opening.
Okay, ma'am.
It's opening.
Yeah.
Have you taken the pictures, Navya?
Yes, ma'am.
Okay.
Ma'am, shall we wait for 5 more minutes, ma'am?
Yeah, yeah. We'll wait.
The feedback form.
Sana didn't join.
No, Sana, she was there, ma'am.
Is there?
She was there, ma'am. Sana was there.
Okay. Let them fill and then leave the,
Yes, ma'am.
that we will know. So when everybody leaves, then we can close.
Ma'am, students who are listening in YouTube, they are also asking for feedback.
Navya, you can,
from-
yes, Navya, you can share the link in that YouTube also, no? You can't.
I'll see, ma'am. I'll just see once. I'll see, ma'am. I'll just see. Ma'am, here also in chat box I can paste, ma'am. I can paste the link.
What, Navya? You were saying something?
No, no,
In
there
chat,
are, yeah.
Ma'am,
in
now,
YouTube also, in chat box I can paste the link. I can paste.
that's
to-
what. That's what. Yeah, yeah. Aparna told me the same thing, that people who are viewing it live, you can, share the feedback link there so that they will fill it there.
Okay, ma'am.
Yeah. So can we end the meeting then?
Still 32 participants are there.
Yeah.
Maybe they have kept it on and left, ma'am. I think so.
Or 7.
Students, those who have filled the feedback form, kindly leave the meeting. Madhuri, Divyashri, Haripriya, Aisha Firdaus, P. Vaishnavi, San. If you have filled the feedback form, please leave, ma. Tejasvi. Akhila, Nikita, Rani, Himaja, Shalini, Kirti. Girls, if you have filled the feedback form, please leave the meeting. Link ma'am has already shared, no, Nikita? Navya ma'am has already put it in the chat box. Where were you? You please check the chat box, Nikita. You'll find the link. Okay. Okay, we'll post it again. We have posted, Nikita. You can fill the feedback. Maybe second year students are there.
Madhuri, Himaja.
Second years are.
Navila. I think they kept it open and left.
So shall we close it off, ma'am?
Yes, ma'am. Only one student is there, ma'am. Second year student. Only 2 students are there.
Shall we?
Not do it
Yes, ma'am.
after coming to college.
What, ma'am?
Santoshi,
Ma'am?
tomorrow can't they do it?
They can do it, ma'am. No problem.
Tomorrow if we share the link.
No, I think it's done, ma'am. There was one girl who didn't get the link. It's done.
Okay, okay.
Shall we end the meeting, ma'am?
Yeah, yeah. Okay,
Okay,
okay.
ma'am.
Good
Bye.
evening.
Bye.
Okay.